Right, welcome back, guys. Today we're going to discuss about first order linear ordinary differential equation that are non-separable. Right? Let's check out the questions now. Right? So in this case, we are given this first order ordinary differential equation x dy dx plus 1 minus 2x multiplied by y equal to x, where the restriction set on the x is greater than 0. Now, our task here is to find the general solution of this differential equation. We have to provide the answer in the explicit form, y equal to fx. All right, now let's take a look at how to work with this. Okay, now first step is to, I'm going to rewrite this again. Okay, so that is basically x dy dx. All right, so that's how it look like. Now, usually is easier if we can simplify the structure a bit. All right. Now, in this case, I noticed that three of these terms do carry the x there. Right. So maybe we can divide this expression left hand side and right hand side by x, knowing that the x is actually greater than 0. So I'm going to divide that. I will have, so that would be 1 minus 2x x here, and then there's a 1, right? So I hope that is clear. Now, from here onward, we notice that this first order ordinary differential equations is non-separable. So what should we do then, right? So here we are going to introduce a function which we call as the integrating factor that will allow us to change the structure of this first order ordinary differential equations into the structures that looks very similar or have some relationship to the product rules. Okay, now what do I mean by that? All right, let's check this out. Okay, now first of all, I'm going to introduce an integrating factor Ix. So I'll call this integrating factor as Ix. I'm going to introduce it to my left hand side and to my right hand side. So that will be, okay. So there you have it. That is the integrating factor that I have introduced into my equations here, which is known as Ix. You can label it anyhow you like. Okay. Now, from here onward, as I said, the intentions is so that this left-hand side structure can be um, sort of convert into something that is relevant to product rules. Okay, now what do I mean by that? Okay, just to recap, product rules state that d dx, if I have two functions of x, u and v, so I can actually write down like u d v dx plus v du dx. Okay, now you can see that this structure here, the Ix form, it looks quite similar to this structure. It has an expression Ix, which is comparable to u here, dy dx, which is quite similar to this structure, dv dx. And then next, we have this Ix multiply with this, which is actually a function of x. That would be comparable to du dx, because when you differentiate a function of u, we would end up with a with an x with a function of x, and then whereby the v would be comparable to y here. Okay, now due to the structures that we have here and the structure of the product rules, now we're going to make a bit of a comparison, and then let's see whether we can obtain any pattern out of this, right? So first of all, I'm going to say that u is a function of x. Bear in mind is actually equal to I here. So I just make it a short form instead of writing ix here. So u is equal to I, and at the same time, I'm also saying that dv dx is actually equal to dy dx, just by comparing, right? Comparing the terms. And then after that, I will say that v should be equal to y. Okay, you can see that from this section here is quite obvious that v is actually equal to y. Okay, so therefore, this v here would be quite similar to y here, whereby the ix multiplied with this function should be a function of x also. So therefore, I'm going to say that my du dx here should be, okay, maybe I'm going to write it down there. It's easier to see here. From here, you can see that my du dx is the same as I 1 minus 2x over x. Okay, so that's what I have at this point of time. Okay. Now, of course, you can simplify this a bit if you like. So that is basically just 1 over x minus 2. Okay. So that's what we have. And then we also knew that u is actually equal to I. So you can see that u is actually equal to I. So therefore, we can replace this u with an I. So I'm going to write that down as um, di dx now as I 1 over x minus 2. All right. So I hope that is clear at this point. Now, the most important technique or the concept involved introducing integrating factor will be step number 1 and step number 2 here. Okay. Now, once you have set up these steps correctly, now the next step will be quite direct. So I'm going to show you at the side here. From equation, considering equations number 2 here, we are actually getting di dx, which is actually equal to I here. And then the interesting part would be you will notice that this is a separable first order ordinary differential equation. Now, how surprising is that, right? From a non-separable linear first order differential equations, we are able to convert that into first order ordinary differential equations that is separable. Right? Now, that is the importance of introducing the integrating factor. The purpose is to convert a non-separable ordinary differential equation into a separable ordinary differential equation. Right? Okay, so from here, we can separate them now. It will be di over I. We can group the I with the di together, where the x we will group them together on the right hand side. Okay, so that's what we have right now. And then, of course, we can perform an antiderivative here. So I'm going to perform an antiderivative both sides. We will get ln I equal to, all right. Now, this part here, we will get a ln x, of course, and then minus 2x. All right. Okay, so I hope that is clear at this point. Now, the idea of applying this method is not to introduce the constant here. So I did not write down plus c or a, because our intention is just to obtain the integrating factor here. Right. So from here, you will notice that we can further write that down as therefore, you will notice that the integrating factors that we need for us to be able to apply the product rule would be these integrating factors can be written as e ln x minus 2x. And then, of course, by applying a bit of exponential rules, we can further trim this down into this one here. So that will be actually x e negative 2x. Okay, now I hope that is clear at this point. Okay, now bear in mind, step number one, number two, and now we have obtained our integrating factors. Now, what I'm going to do next would be, I'm going to revisit my product rule one more times. Here I'm going to call that P because it's product rule. So I'm going to revisit my product rule one more time, and then I should be able to solve this first order linear ordinary differential equation. Okay, now I'm going to proceed on from here, and then I'm going to refer to the product rule. Okay, now stay tuned. All right, as I mentioned, previously we have already found out our integrating factor, okay, which is indicated by this equation number 3. And then we derive that by making use of the product rules. So now we are going to substitute our integrating factor into the product rules that we have set up at our earlier stage there. So we notice that the u is actually represented by integrating factor I. So instead of writing that as u, now we are going to change it back to I instead. And then next, the v. What is v? We have already identified that v should be the same as y. So therefore, we're going to convert the v into y now. Okay, and then that would actually give us the left-hand side expression. All right. Now, how does that look like? Let me clean this up. Okay, I'm going to rewrite this integrating factor at the side here just for reference so that we can refer to it shortly. So this integrating factor is given by here. Okay, I'm going to keep it there. All right. So from here, okay, from here, we know that the u is equal to I, just to recap, the v is equal to y here. So I can rewrite my left-hand side expressions for equation number 1 as, okay, so from 1 now, I can restructure this, the whole left-hand side expressions into something like this now. All right, I know that my u is equal to I, so I'm going to write that down as I. And then I know my v is equal to y, so I'm going to write that as Iy now. And then on my right hand side, it remain as I. Okay, so that's what I have right now. Okay, so from here onward, this also become a separable first order ordinary differential equation. So now we can apply the same strategy. We can write down Iy, okay, is actually equal to, so we can actually I'm going to rewrite, okay, let me erase this. I'm going to rewrite the expressions slowly so that you can follow up. So in this case, we can rearrange this, become I dx. Okay, and then after that, we're going to perform antiderivative both sides. And then the left hand side would certainly be Iy in this case. And then our right hand side would become the integrations of our integrating factors, which is this one here. So that will be x e negative 2x dx. All right. So I hope that is clear. Right. Now, if you refer to our left-hand side expression, this require another integration technique, which is known as integration by parts here. Okay. So I'm going to label this as equations number 4 right now. Okay. All right. So this part, I'm going to pause for a while for you to check back again what we have done so far until we reach this section here. All right. Now next, I'm going to work with this equations number 4 now by performing integration by parts for my left-hand side integration. Hopefully at the end, I should be able to obtain the general solutions of this differential equation, right? Okay, so just let me erase all this. We don't need this anymore. Okay, all right, so now we are ready. Okay, so from here, from equations from 4, I can write down I is actually equal to this. Okay, integration by parts. All right, let's consider the right-hand side expression. Okay, so right-hand side expression, I'll just write down right-hand side expression here. Okay, so that we are referring to this section here. Right, now we're going to let, first of all, I'm going to write down at the side, I'm going to let u be x, and then the dv dx equal to e to the power of negative 2x here. Right. And then from here onwards, I will know that my du dx would give me a 1. Okay, that is very clear. And then after that, my v, by performing integration here, I would be able to obtain negative 1 over 2 e negative 2x here. All right. So I hope that is clear. Now, once you are ready with this, okay, now once you're ready with this, maybe I don't need to write left-hand side or right-hand side. From here onwards, your integrations of your right-hand side expression, e negative 2x dx, can be written as, based on this formula, it will be uv minus of what you have here, v du dx dx integration. Now there's a formula for integrations by part. So from here, I'm going to substitute all the expressions that I have worked out. So u is a x, and then my v is negative half e negative 2x. Okay, and then I'm going to substitute that into here also. Therefore, it will become a half e negative 2x dx integration. Okay, so just let me check whether I got it correct. All right, so there you have it, right? So from here onward, I'm going to perform the integration one more time. Yeah, one more time. So in this case, I will get this. All right, now the integrations for this is definitely 1 over 4 e negative 2x then. Okay, now I have indirectly completed my integrations by part. Now all I need to do is go back to my previous sections here, so which is equations number 4. So I'm going to continue from there. Therefore, I can actually write down that as Iy now is actually equal to, yeah, negative half x e negative 2x minus 1 4 e negative 2x. Then again, we know that we knew about our I. Okay, so our I is basically x e negative 2x. So therefore, I can write down x e negative 2x y is equal to negative half x e. All right, so there you have it at this point of time. Now that will be our um, incomplete. I would say that it's still incomplete um, implicit implicit general solutions for that first order um, ordinary differential equations. So how do I make it explicit then? So in this case, how do I make it explicit then? All right. So this is what I'm going to do. Let me erase all this. Okay. So from here onwards, I can rewrite this as, so from here I can divide both sides by this x exponential negative 2x. So therefore, I'm going to rewrite here. Before that, I'm actually having this. Okay, so that's what I have. So now I'm going to divide both sides by exponential negative 2x. I will end up with this. Oops, my ex is gone, so I shouldn't write that anymore. Okay, so that's what I have currently. If I divide both sides by e negative 2x. Okay, and then now at this point of time, okay, the other thing you have to remember is after your integration by parts, we do not put in the c here, right? Okay, so this is what we have after we divide by exponential negative 2x, and then we are almost done. Therefore, the y is equal to negative half minus 1 over 4x here. All right. Now, I think from this point onwards, hold on. Yep, I think I forgot my plus c. Yes, correct. Okay, that's my main mistake. Sometimes we carry out this integration by parts, we may entirely forgot our c here. So there is a c. Okay, so please forgive me on that. There's a c, so I recognize that there's a C, so therefore you have to put a C here, and then therefore there's a C here, and then at the same time there's a C there also. Never mind, it's a good time for us to check on our error. Okay. Okay. So here we have a C, and then therefore there's a C here also. Yep. So from here, after we divide both sides by exponential negative 2x, we should have C e 2x then. Okay. Now it's perfect. And then after that, I'm going to divide both sides by x because knowing that x is greater than 0, so therefore I will have this uh, plus c over x exponential 2x there. And then that will be our general solutions for our first order ordinary differential equations. All right, so I hope that is clear for this tutorial. All right, if you like what you are looking at, don't forget to click on the subscription button and then turn on the notification bell so that you can receive the latest video. Right, thank you very much for watching. Until I see you again. Take care, everyone.